Yes. Okay, we're talking about infinite limits. So the limit as x approaches number, is our graph going up to positive infinity or down to negative infinity? And of course, if they're going to the same place, then the limit is that thing. So these three, A, B, and C, we're all going to graph on this same little coordinate over here. Okay, so hopefully you recognize this as a rational graph. Okay, the graph of a rational function with a domain restriction of x cannot equal positive 3. Okay, because if you plug positive 3 into your equation, you're going to get a 0 in your denominator. And from pre-cal, we learned that whenever we have a 0 in our denominator, we have a vertical asymptote in our graph. Okay, so this is a sketch of the vertical asymptote, right? The vertical asymptote goes through positive 3. And then because this is a bottom-heavy function, right, we have an x in the numerator and an x in the denominator and a 1, or an x to the 0. That means we have a horizontal asymptote through your x-axis. Right, so we have a vertical asymptote at positive 3, or x equals positive 3, and we have a horizontal asymptote at y equals 0. Okay? So it's kind of important to understand about kind of what this graph is going to look like to begin with, as we're talking about the limits as x approaches our asymptote from the left side. Okay, so we have two options. Either your graph goes up or your graph goes down. Okay, so what we're going to do is we're going to plug in one value pretty close to negative 3. So I'm going to plug in maybe 2.9. Okay, we're going to evaluate what is the y value when x is 2.9. Okay, that's pretty close to positive 3, right? That is a number close to positive 3, but on the left side of positive 3. Okay, and you can literally pick any number you want to, but I think just for demonstration purposes, 2.9 is a pretty decent number. So if I do 2.9, that's 1 over 2.9 minus 3. So the question is this number positive or is this number negative? Negative. So 1 over negative 0.1, right? 2.9 minus 3 is negative 0.1. Right? If you bought something for $2.90 and you gave them $3 in cash, they would give you a dime back, or 10 cents, 1/10. And of course, 1 divided by 1/10 is negative 10. Okay, yes, it's wonderful that you get an answer of negative 10, but the better thing is that the answer is negative. Okay, the important part is that our answer is negative. When I plug in 2.9, I get a negative value, which means over here on my graph, okay, if 2.9 is negative and it can't cross my red line and it can't cross my black line, then where does my graph go? It has to go down. My graph has to go down. And what is the limit if my graph goes down? Negative infinity, right? As I get closer and closer and closer to 3, so 2.9 and 2.99 and 2.9999, I'm going to get a bigger and bigger negative number. So on the left side of x equals 3, left side of my asymptote, the graph is going down to negative infinity. That's the important part. Okay, now what if I were to pick a point to the right of positive 3, right? Because this is what this little plus means, to the right of positive 3. So how about if we pick 3.1, right? That's a number pretty close to positive 3, but on the right side, just so we can see what the y values are doing. So 1 over 3.1 minus 3 is 1 over positive 0.1. Okay, 3.1 minus 3 is a positive value. That's the key, because positive values are above the x-axis. So at 3.1, my graph is up there. So if I were to approach positive 3 from the right, what do my y values do? They go up. So the limit on the right side goes up to positive infinity. So the fact that it's 10 is my answer is nice, but the better part is that it's a positive value. So on the right side of my asymptote, the graph goes up to infinity. On the left side of my asymptote, the graph goes down to negative infinity. So what is the limit at exactly positive 3? Well, because the left side goes up and the right side goes down, wait, switch that. The left side goes down and the right side goes up. Those aren't going to the same place, so the limit at 3 exactly does not exist. Okay, so scratch off that equal sign. The limit does not equal, right? Limit equals, no, limit does not exist. So scratch off the equal sign for that type of a problem. Because the limit exists when both the left side of the graph and the right side of the graph go to the same y value. And positive and negative are not the same. Okay, part D. This one's going to go for our single graph right here. What's the difference between A, B, and C now and part D? We have a square value. What does squaring something do numerically? Multiply it by itself, and what does that do to the sign of anything? Negative 3 times negative 3 is positive 9. Negative 12 times negative 12 is positive 144. So squaring something makes values positive. Okay, that's an important thing to understand. So if I'm looking at positive 3 as your asymptote, because it is, you still have a 0. If x equals 3, then you still have a 0 in your denominator. So we still have an x not equal to 3 domain. And we're still using that same idea. So I'm plugging in a 2.9 to see what's happening on the left side as x approaches 3 from the left. And I'm still plugging in a 3.1 to see what is happening as x approaches 3 from the right. Okay, so I still have to do a left side and a right side limit to see what's going on exactly at this asymptote of positive 3. Okay? So let's do 2.9. 1 over 2.9 minus 3 squared. Okay? That's 1 over negative 0.1 squared. Negative 0.1 times negative 0.1 is positive 0.01, I believe. Right? But the fact that it's a positive is the important part. Anytime you square something, we're going to get a positive. In other words, we're never going to get a negative in this denominator. So will our y values ever be negative? No, because squaring things makes them positive. So on the left side of our asymptote, the graph is going to go up to infinity. And then also on the right side of our asymptote, the graph is going to go up to positive infinity. So if both of our left side and my right side are going to the same spot, positive infinity, that means the limit as x approaches 3 is going to be positive infinity. Okay? So in order for a limit to exist, the left side and the right side have to go to the same place. In this case, positive infinity. Okay, so here is our weird graph, the absolute value of a linear over that same linear. Okay, so I don't know if you remember this, but we get 2 straight lines, right? 2 horizontal lines at positive 1 and at negative 1. Okay, so let's just go over and verify that real quick. Let's see, positive 2 is what we're looking for, so x and y. We'll go with 0, 1, 2, 3, and 4. So these will be our x values for this graph here of absolute value x minus 2 over x minus 2. Okay, so when I plug in 0, that's the absolute value of 0 minus 2 over regular 0 minus 2. So on top, absolute value makes things positive. So 0 minus 2, yes, that's negative 2, but in absolute value, that becomes a normal positive 2. But in the denominator, I have a negative 2. So positive 2 divided by negative 2 is negative 1. Okay, and then the same thing for 1. 1 minus 2 in absolute value over 1 minus 2. So 1 minus 2 is negative 1. So in the denominator we have a negative 1, but in the numerator, in absolute value, it becomes a positive 1. Positive 1 divided by negative 1 is negative 1. Okay, and then at 2, of course, 2 minus 2 is 0. 0 over 0 is undefined. So at 2, we have our undefined value, right? Slash asymptote, or whatever. But then what's 3 minus 2 in absolute value divided by 3 minus 2? Right, that's positive 1 over positive 1, which is positive 1. Okay, and then 4 minus 2 over 4 minus 2 is 2 over 2, which is 1. Okay, so anytime we have this situation where we have an absolute value divided by itself without absolute value, we have two linear equations. One horizontal line through positive 1 and one horizontal line through negative 1 with an undefined value at 2. Okay, so if we have negative, let's see, what do we have? 0 and 1, those were negative 1s. So you have a horizontal line, y equals negative 1 to the left of positive 2, and we have a horizontal line, y equals positive 1 to the right of positive 2, with, of course, an open circle on both of these lines at x equals 2. Okay, because that's where your asymptote would be, like that. Okay, so it says, what's the limit as x approaches 2 from the left? Right, as x approaches 2 from the left, we're getting closer and closer to a y value of negative 1. Okay, because that's the y value everywhere to the left of positive 2. And how about the limit as x approaches positive 2 from the right? Is positive 1. Okay, because we're coming in this way, we have a 1 value, a 1, a 1, a 1, a 1. As we get closer and closer to 2, right, 2.1, 2.01, 2.0001, the y value is still positive 1. So if we evaluate this from the right, we go to positive 1. From the left, we go to negative 1, right? So the left was on top here. Left, we have a limit of negative 1. Right, we have a limit of positive 1. So what's happening exactly at 2? Does not exist. The limit at 2 does not exist because the left side and the right side don't go towards that same value. Okay? Now I want to add in a couple extra things because I don't know if you've ever seen this before or not. Okay, this is a fancy function called the step function. Okay, the step function, or sometimes called the greatest integer function. Okay, the greatest integer function. Okay, the way that our life works, right? Think about ages. Think about your age, right? When you say your age, are you overestimating or underestimating your actual age? Underestimating, right? Because exactly on your 16th birthday, that's the day that you are exactly 16 years old. What about a month later? You're still 16 years old, right? You don't say I'm 16 in 1 month. You say you're just 16. What about when you're 16 and 360 days? You still say you're 16 years old, right? That is a least integer function, okay? Because if this is your years, right? This is your years that you've been on the earth, 16, 17 years. Anywhere between your 16th year and your 17th year, we are 16 years old, right? So 16 and a half, you say you're 16. 16 and a quarter, you say you're 16. 16 and 2 days before your birthday, you still say that you are 16. But once you turn 17, ooh, now you are 17 years old on your exact 17th birthday, and now for a whole year, you're 17 again, even though you're 17 in 4 days, and 17 in 30 days, 17 in 200 days. Okay? So this is the way that these step functions work. The post office often has a step function for pricing. Any letter between 0 ounces and 20 ounces costs 45 cents to mail. Anything between 2 pounds and 4 pounds costs the same amount to mail. Right? You don't pay per ounce very often. You pay on a step function. And these look weird. I think it has this, like a double bracket around it or something. It looks very, very strange. We don't really see this. This is the notation for your step function. Okay, the notation for your step function looks like that. So what if we were looking at the limit of a step function? So the limit as x approaches 17 of our step function, the greatest integer function x. Okay, so as x approaches 17 from the left, as x approaches 17 from the left, so as you're going towards your 17th birthday, what age do you call yourself? 16. You call yourself 16. Okay, so as you approach 17 from the left, your limit or your age is going to be 16. But what about if we talk about the limit as x approaches 17 from the right? Right, so once you turn 17 and you're looking back, oh, a week ago I turned 17, right? Because if you're approaching 17, you're still 16 years old. But once you have your birthday, by golly, you are 17 years old. Okay, so if the left limit is 16 and the right limit is 17, what can we say about the limit as x approaches exactly 7, or the limit at 17 itself is non-existing? Okay, so there's lots of functions where, I don't know about lots, but there are some functions where the left side and the right side are good, but then the limit exactly of that number does not exist. And this is good for all integers, right? Every integer, the limit does not exist for your step function, especially if we're thinking about age. So this has a limit that exists everywhere except for at the integers. So 17, 18, 19, 20, at all integers, the limit does not exist. Okay, just something I wanted to introduce you to, because I think there's some problems about step function on your assignment tomorrow. Okay, pretty interesting little thing.